switch the recording system so people can hear the questions afterwards.
Yeah. Yeah.
Good morning, everyone. I'd like to introduce.
No. It's not on,
no,
right?
they can hear me through the. They can't. I guess I have to speak loud enough.
Oh.
Oh, it is? Okay. Oh, on the bottom, you said? There we go. Okay, we got a green light.
Yeah, there you go.
Okay, good morning, everyone. I'd like to introduce our speaker, Pallab Bhattacharya. He'll be speaking on quantum dot, nitride quantum dot and nanowire laser sources. He's a professor at the University of Michigan in Ann Arbor and has written a book, Semiconductor Optical Devices. He has many awards, too many to list in a short meeting, but he's a member of the National Academy of Engineering. Please welcome our speaker.
Yeah, this is on. Oh, okay, all right. You can everybody hear me? Yeah, right. All right, so right, good morning. You know, you come to California in January or February and from a place like Michigan, and that's when you realize what California is all about. So this morning I saw this sparkling day and realized that California is different. So anyway, let's get down to business, and I'm going to talk about 3 nitride quantum dot and dot in nanowire light sources, and mainly lasers. I was telling somebody earlier today that my foray into the nitrides it's really an accident. But so why do we want to use quantum dots in the nitride system? I'll give you a brief background of that. The molecular beam epitaxy and characteristics of self-organized InGaN GaN quantum dots. I'll give an example with 2 devices. One is an interesting device. It's a white all quantum dot converter white LED where we don't need to use phosphors and all that. And then red lasers. Red is a color that's very difficult to achieve with quantum wells. And then I'll move on to the other nanostructure, the disk in nanowire heterostructures on silicon. And the key thing here is it's 001 silicon. And then I'll talk about the passivation of the nanowires, the evidence of forming dots in the nanowires, and then edge emitting visible, and we can go all the way to near IR. So, but before I go into the nitrides, I'll just spend a minute into the last bit of work that my group did with the indium arsenide quantum dots, and there's a reason I show all this. So first of all, on indium phosphide, it's not easy to grow quantum dots. If you try to grow self-organized quantum dots, they end up as what people called quantum dashes, because the kinetics was so driven on the surface, and it's quite challenging to be able to grow quantum dots. And as far as I know, there were only 2 groups that really, Reithmeier in Germany and our group, succeeded in growing these quantum dots. And then of course we added all the frills, modulation, doping, p-type in the quantum dots, and tunnel injection and all that, and got really good lasers. As you know, in 1.55 micron lasers, at least commercially, they use quantum wells, and the worst feature of those devices is the T0. The T0s are very small. The I threshold has a large temperature dependence, but in these lasers you can see the T0s are very high. and you can get very respectable powers, you get good modulation bandwidths, very low chirp, and this is one thing, this is the result I really wanted to show. The alpha parameter, it shows this singular dip at the lasing wavelength, and this was predicted theoretically, it's been observed experimentally in quantum dot lasers, and this is related to the peaked gain spectrum in quantum dots. So this is a very singular feature of quantum dot lasers, that the alpha parameter shows this dip. So that's all I'll say, and we'll come back to that dip later on. So quantum dots, InGaN, GaN quantum dots, why do we want to use them? These two publications or work came to my attention. One was by Ewan O'Reilly in Ireland, and these are theoretical plots of the built-in polarization potential comparing quantum dots with quantum wells. And you can see, and so what he used, he modeled them as lens-shaped quantum dots about 4 nanometers in height and 20 nanometers in diameter, and you can see for the same composition the polarization field is much smaller, and it only becomes comparable when the composition, the indium composition, is doubled. And this is because the dots, essentially self-organized dots, they form by strain relaxation. And these are calculations by my former colleague Jaspreet Singh and his group, where they calculated the radiative lifetimes for dots of different composition and different size, namely the dot height. And again, you can see that how they vary with composition and height, and mainly the difference is brought about by the overlap or lack of overlap, the electron and hole wave functions. The important thing is that here you see that the lifetimes are of the order of a nanosecond, whereas for comparable quantum wells the lifetimes are much larger. So both of them really point to the fact that you have much smaller polarization fields, and therefore one can expect much smaller Stark effect and Stark effect related effects in devices. So I knew that that this was a good system to try and grow quantum dots and look at devices. And we could bring in all our experience with the indium arsenide dots. And here is a very simple experiment with an LED-like structure where we actually measure the polarization field. And these are green-emitting dots, and we see that the polarization field is about 90 kilovolts per centimeter. In green-emitting quantum wells, it's over a megavolt per centimeter. So we were not really the first ones to grow quantum dots in this system. In fact, some beautiful work had been done by at least a couple of groups. And here are some results. This is from Nicolas Grandjean's group, very early work. And this is the thickness composition phase diagram. We kind of use it as a guidance to grow dots. So all the dots are grown in this part of the diagram. And this is another paper where you see the formation of the dots by Reed. And so initially you see the specular spot, the oscillation, and then there's the juxtaposition of the Bragg spot that appears, and you see the formation of the dot. After about, and this is for a 35% indium gallium nitride composition, and you have this 1.7 monolayers of wetting layer, and then the quantum dot is formed. And this is a histogram of the dot island height, and it's typically about 2.9 to 3 nanometers in height and about 27 nanometers. So the aspect ratio is 1:9. So they are fairly sort of spread. The thing that caught my attention in this paper was the fact that they had done several things. So they said that you can grow quantum dots as long as you are above 18% in indium. And you have to grow under nitrogen-rich conditions, and so on and so forth. Now, this 18% caught my attention, so we did a quick calculation, and we found that that translates to about a misfit of 2%. And years and years and years ago, we had published a paper in 1988 to be exact. It was a sort of gave a quantitative basis for the formation of quantum dots, and this is a formula that a very simple formula. N is proportional sort of number of atoms to the height of the dots. W1 and W2 are the nearest neighbor and second nearest neighbor bond energies. R0 is the substrate lattice constant, and dc is the critical thickness. And this formula told us then that if dc is less than about 10 to 15 monolayers, which is about 2% for that system, then you will have quantum dots. In fact, this result and paper was reviewed by Pierre in Physics Today, and it appeared in January 1989. So it's like the 2% rule, and I was pleased after so many years to see that, and we knew that this was almost universal. It should hold for any mismatched system, and sure enough, in this also 18% translates to, in the nitride system, exactly 2%. So that was really good. So I knew that, well, we definitely can grow Stansky-Castronow self-organized dots with wetting layers and all that, and so we moved ahead. So these are some of our typical, we do it by molecular beam epitaxy, typical growth conditions. It's a little different now. We use higher nitrogen flow rates than what is shown here. The gallium nitride, the gallium and indium fluxes are about the same, and so on. So we grow, these dots are grown under nitrogen-rich conditions, and these are some some AFMs of blue dots and red dots. The scales are a little different, so it can be a little misleading. They are not that sparse or that large, although the red dots are a little larger than the blue dots. The densities, the areal densities are about the same. We also saw that growth follows a kinetically driven law, and here you see the line shape function for a scaling law, and here you see the scaling function for the height distribution of the dots, and we find that as we increase the temperature, for example, I is a parameter proportional to the size or the height of the dots, and we find that as we increase the growth temperature, I increases. For example, when we go from say 450 to 550 growth temperature, I increases from 3 to 5, and so on. So these dots so the growth is kinetically driven. We found something very interesting, which at least we have never seen in the arsenide dots, in that when we were growing multiple layers of dots, and so we would stop the growth after first layer, or growing up 2 layers or 3 layers, and so on, and we found that the first layer of dots was very sparse, like 10 to the power 7 dots per centimeter square, and after that the density quickly increased and stabilized after about 3 dot layers. Now, this first layer, it was actually turned out to be very useful for us. I mean, when we were trying to make, say, things like devices like single photon emitters and all that, it turned out very useful, the dots being that sparse. So this is all captured in here. Here you can see that the average density of the dots. So after about the 3rd layer or so, they kind of saturate, and the height also follows a similar trend. And after about the 3rd layer, these experiments were all done for red-emitting dots, but this micrograph is really for blue-emitting dots. But we see that after the 3rd layer, there is very good vertical organization. So to explain all this, my colleague Joanna Milinchek, she used this DeHace kind of model, and basically what it translates to is that if you use the critical strain energy rather than the critical composition, you can't use the composition because the composition is varying. So if we use the critical strain energy, what it means is that the amount of time that is spent in growing the dot is actually very small for the first dot, and so that times the nucleation rate. If the nucleation rate is constant, then this translates to a larger dot as we proceed, and then it saturates. And in fact, their group did atom probe tomography, and you can see a similar trend that from the first to the second to the third, there is a steady increase in the indium composition, and then it kind of stabilizes.
When you say the composition as a function of thickness is changing, if you go back to your last slide, where is it changing? So,
No, the composition is not changing. Yeah. Yeah, so what I'm doing is, you see this time. So this thickness translates to time, basically, the time spent to grow the dot itself. So there is a critical thickness where you have two-dimensional growth, and then there's the three-dimensional growth. So this time spent in the first dot is very small. So time times the nucleation rate is the, yeah. So we did a lot of things to make them device worthy. Of course, you have to do a lot of things to optimize the dots, mainly their quantum efficiency and so on. So we varied 3 parameters. One was the indium gallium nitride deposition thickness. The nitrogen, we did an interruption after growth of the dots, and this allows the organization, the movement of the air atoms to form the dots and so on. And if the interruption time increases, then the size of the dots increase. And then the gallium nitride barrier thickness, and this changes the strain distribution and all that. So at the end of the day, what we are trying to do with these 3 parameters is to change the size, the composition, and ultimately the electron hole overlap and the quantum efficiency. So here is an example, just one example of where we hold the gallium nitride barrier thickness constant, the interruption time constant, and we vary the InGaN dot charge thickness. And you can see how the radiative, and so we do time resolved and temperature dependent photoluminescence and kind of get a relative idea of the lifetimes from those 2 experiments. And you see the radiative, non-radiative, and the total lifetimes. And here you can see the internal quantum efficiency and the peak wavelength. As the dot gets larger, you can see that the wavelength also moves to longer wavelengths, the emission wavelength. And you can see here you have the optimum electron hole overlap, but if the dot becomes too large, then of course the overlap decreases. So under these conditions, for example, with InGaN thickness of about 8 to 12 monolayers, and here in this system roughly 8 monolayers is about 2.2 nanometers. So that's something I remember. And so you can see we get about 49 to 50% efficiency in these as grown dots for these red dots with average height of about 4 nanometers and base width of 65 nanometers. And here are some other results. So you see the variation of the line width of this is just as a function of temperature, and so this is the inhomogeneous broadening right here, and what you see this as an increase, that's the homogeneous broadening with temperature. And then from EDAX measurements, TEM EDAX, one gets the composition. And for red dots, we nominally the indium composition is about 40%. I'll move on to one. I mean, there's a lot more we obviously have done in the growth and the characterization. I made it sound so simple. It's not that simple. So here's an interesting device. Now, as you know, and here I'm preaching to the choir, obviously, current white light sources, they are made with blue LEDs exciting red or yellow phosphors. Now, in these phosphor converted LEDs, you have all kinds of losses. You have conversion losses due to Stokes shift. You have backscattering of the converted and the incident light by the phosphor layer, and then you have non-radiative internal losses, and then of course you have problems with temperature stability and reliability and so on. So it would be nice if you could have an all semiconductor converter white light source. And now that we can grow red dots or even beyond, I mean as that early paper said, you can grow dots even with 100% indium. We haven't gone there, but it can perhaps be done. So, so what we do is we place these red emitting dots or multiple layers of those in this contact below the contact layer. So it's a passive set of passive dots, and these are excited by these blue emitting dots, which we call the active dots. So the red dots are the converter dots, and the blue dots are the exciting dots, and so that's the PN diode there. And we put a aluminum reflector at the bottom at the end after processing, and that's the chromaticity coordinates there for, and we had made a variety of devices where we vary the blue and the red dot compositions and therefore their emission wavelength. This is the EL. If you measure a typical device, that's the kind of EL we get, and so with that we can vary the chromaticity coordinates, can really fine tune it, and at the end of the day the correlated color temperatures, and we can go all the way from warm white light 4400. I mean we could if we carried on the experiment and tuned this red, the blue and the red a little more, we could have gone to 3500. We know that, and all the way to cool white light. And the other good feature is that you see the color temperature, the variation of that with the current density is very, very small, and this I believe is due to the small the polarization field and therefore the small Stark effect shift in these quantum dots. So this work was really done in collaboration with Osram in Regensburg, and they are now prototyping this in their lab. Okay, so let me move on to the lasers then. Before we made red emitting lasers, we did green and blue and many others, but the red was of interest because amongst other applications, red lasers so the auto company came to us and say we need these red lasers for heads-up displays, but the requirements were very, very demanding. They need to operate at high temperatures, so and then with output powers of 70 milliwatts and thresholds of about 2 kiloamps per centimeter square. And the existing red lasers, as many of you may know, currently red lasers are made with this indium gallium aluminum phosphide AlGaS based devices, and they have two. If you look in the literature at least, you'll see two things. One is the threshold currents are very high and the temperature stability is very poor. Now there's this company, of course, they before they gave us the contract, they came to our labs, they actually saw an operating device before they even would sign the papers. And what I did promise them was that, okay, so it may not, we make lasers at the end of the day, it may not work at 95 degrees, but they'll certainly work during the winter in Michigan. So that was the promise, but here's a device actually working at 95 degrees. This is CW operation. The size of the device, which I forgot to mention here, it's about it's a 5 micron range and 1 millimeter in length. The facets are not coated; they are just cleaved facets. So there's no DBR or reflector in the facets, and so that's what you see at CW. And with pulsed, so here is the variation of the threshold current density, And so in the structure, I should say a couple of things. We use indium aluminum nitride cladding, 18% indium, and that's about equivalent in band gap. That's about equivalent to the offset that we get to about 46% AlGaN, and 46% AlGaN is full of strain. So this is lattice matched, and growing this is very tricky. You have to grow it at a low enough temperature that the indium doesn't go flying, but have it sufficiently high that the aluminum has some chance to move around and get incorporated. So we found a temperature of about 490 in these structures is good. And so you have the waveguide, as you can see, is very dilute InGaN, and then you have the electron blocking layer, and this spacer thickness is a very tricky parameter, and we varied this all the way from 15, 20 to 60, 70, 80 nanometers. And what we are doing with that, I believe, is just changing the band alignment and the band bending and all that, and ultimately the keeping the electrons in place. And so we find that for 60 nanometer spacer we get the best results. And this is pulsed operation with a 1% duty cycle, and we can get to reasonably high powers. Now you'll have to realize, and I'll show you some modeling of this very soon, that these, when we characterize the devices in the lab, there is no active cooling, there is nothing. This is just basically the laser sitting there and the probes and so on, and you'll see how hot they get. But in spite of all that, these results are extremely encouraging. Just to calibrate you, the differential gain is about an order of magnitude smaller, maybe a little more, than the best indium arsenide quantum dot lasers, but that's because of the materials, the nitride materials and so on. But what is very encouraging is the T naught values, which are way larger than the indium gallium aluminum phosphide lasers. If you can grow quantum dots, you can, or make lasers with them, you can do other things too. And one measurement you can do is measure OJ recombination. And the way you do it is by using this formula, which comes from the rate equations. You measure the delay. You do large signal modulation, and you measure the delay between the electrical pulse and the optical pulse. And here you see the characteristic oscillations that one should, and by measuring the delay as a function of current and so on, and you analyze it with these relations, and you need two things: the spontaneous emission factor and the radiative recombination rate and the non-radiative recombination rate. We get the radiative recombination rate by a k dot p calculation on the band structure, and the non-radiative recombination, we actually went in and did deep level transient spectroscopy measurements and measured characterized the deep levels, determined their density, and from the density we measured ANR. So these are the OJ coefficients that we get in blue, green, red. Do you have that pointer? It's gone now. Mine has died. Yeah. So these are the values that we get, and if you can recall, in the early days people were measuring abnormally high values of the OJ coefficient in these nitrides, and there are lots and lots of theories about why they were so high, and I'm not going to get into that. I believe it was some sort of a defect assisted OJ that was being measured there, but now we seem to be measuring, this is a graph plotted by Piprek, and we seem to be measuring the OJ coefficients at least in the right place. So that's another experiment you can do with these quantum dot lasers. Now let me provide some theoretical validation of some of our results. So we were collaborating with S.L. Chuang, and many of you know he passed away, but he had trained his student very well, and John Dalasasi took over, and so he's been continuing. This collaboration has been very good. So they model based on structural characterization. The dots they model as truncated hexagonal pyramids. The strain distribution was calculated using linear elastic theory. There are other ways of taking the strain into account. For example, the electronic states was calculated with a single band effective mass Hamiltonian, and the effective mass was further refined with an 8-band K dot P calculation, and then the gain spectra is calculated by Fermi golden rule, and then the temperature dependent light current characteristics were calculated from temperature dependent rate equations. So here you see at the bottom here a variation of the emission wavelength as a function of current density, taking into account both the Stark effect and the heating effect. And what we get from here is a measure actually of the Stark effect and the residual strain, and the residual strain in these red dots are about 1.1%. So there is still the strain in the dots. And here you see they have tried to fit our measured gain spectra, and again this is as a function of temperature, and you can see they can fit our measured gain at about 120 degrees centigrade. So the devices are really heating up, and that is one reason why their lifetime, and I don't mean carrier lifetime, I mean their lifetime on this planet is small. So we just measure all the measurements we can do till they die. So there's 58 MeV or so of inhomogeneous broadening, and then the disagreement at the lower photon energies is due to compositional inhomogeneities and size variations and all that. And there you see the fit of the LIV characteristics. So we get some very valuable information about the material from these analyses, about the materials, about the devices, about the heating, and how to design future devices and so on, and so we are following up on this. Yeah, so there's a whole host of problems. One is we of course the devices are very hot, and the way we are measuring it and so on, the devices are getting incredibly hot. One. Two, our contact technology is by no means perfect. I tell the students it's really crude. We have to learn how to make decent contacts. Three, we don't use Sumitomo substrates or anything even close to it. We are using fairly crappy substrate with 10 to the power 6 dislocations. So those are, I believe, some of the overriding reasons. We have checked though that once we grow the laser heterostructure, we have done dislocation density measurements after growing the dots. We don't add a whole lot of defects in growing our structure. So if we could, for example, grow on say Sumitomo substrates and all, they would be incredible devices. And it is based on that promise that this auto company has taken it on to the next stage. They are going to develop it in their own lab now. So that's a good question. All right, so with that I'll leave you with that. So at the end of the day, with these results and the power output and everything else, they were satisfied, and as I said, they are taking it on for proceeding with development of these lasers for heads-up displays. So if you see cars with red heads-up displays and drivers crashing into trees and so on and so forth, which I believe people will do when they have these heads-up displays, you can blame it on me. As if we don't have enough distraction in a car already. So the other fascinating nanostructure I'm going to talk about are these nanowires. I'll be the first one to admit, not too long ago, some colleagues of mine and we used to sit at conferences and we used to laugh at nanowires. Whenever there was a paper on nanowires, I did not believe they would go anywhere. I just didn't. Till one day a postdoc of mine, unknown to me, he was supposed to do other things, which he did, but he also started growing these nanowires. And then he came to me and showed some of these TEMs and other things, and they were just incredible. What caught my attention was that these nanowires are free of extended defects. They really are free of, and we have hundreds of sort of lots and lots of evidence of that in different experiments, characterization experiments, in devices and so on. Again and again we see the results we get can only happen because they are free of extended defects. And I'll get more into that. And so it's not only a good, it would be a good platform for doing fundamental material studies, anything. I mean, we measured, for example, spin relaxation times in InGaN disks in GaN nanowires, made spin valves from single nanowires, LEDs, lasers, as you'll see, and so on and so forth. So, in fact, it's the best nitride material that you get, actually, epitaxially, that you can get. It's that free of extended defects. Now, you can create defects very easily. I mean, if your growth is not optimal. So now and this happens because of the large surface to volume ratio. Also, the radial relaxation of strain during epitaxy, it reduces the polarization fields in the heterostructures and so on. We've measured OJ coefficients by an optical technique, and the results agree very well with what I showed you before and with things in the literature. We have done Schottky diode. We've made Schottky diodes on the nanowires and measured the barrier heights, and the barrier heights scale with the indium composition in the nanowires. The surface recombination velocity, this was done by another group. The surface recombination velocity in these nanowires is at least 2 orders of magnitude smaller than that on the gallium arsenide surface. Now, the gallium arsenide surface, of course, the recombination velocity is very high, 10 to the power 5 centimeters per second, and this is about 10 to the power 3. And then you can put InGaN disks in these nanowires, 2 to 3 nanometer disks, and you can vary the composition in those disks, and you can get any color you want in the emission, all the way from ultraviolet to, and you'll see how far. So it does present, and as you'll see, you can grow it on anything. And this is not a catalyst induced growth like gallium arsenide nanowires and silicon nanowires and so on. This is catalyst free. So there is no gold ball riding up with the nanowire and with which you can do nothing. So a word on the growth of the nanowires. And this has taken the work of a lot of people actually to really understand what goes on in this catalyst free. So initially, when you bring on the fluxes, there is a preferential bonding of silicon with nitrogen, and there's a huge gallium desorption. The gallium is all dissolved, and the silicon nitrogen bonding creates this very thin silicon nitride layer. And this silicon nitride layer does many things. One, it removes the epitaxial constraint of the substrate, and therefore you can grow it on 001 silicon, you can grow it on 111 silicon, on other templates, whatever, you always grow these nanowires because there is no epitaxial constraint of the substrate. The silicon nitride also greatly reduces the 13.5% misfit on the substrate, greatly reduces the defect density at that interface, unlike bulk, unlike two-dimensional growth. And so now the air atoms, and what happens is that the temporal strain distribution on this nanowire creates the time varying strain distribution, creates these nucleating points for gallium nitride clusters, and then on these clusters the growth of the nanowire starts parallel to that silicon nitride layer, and then there's a lot of gallium desorption. Yes?
Infinite
Sorry?
Is there random in-plane rotation of the nanowires? Since you have no epitaxy, does it mean they're actually all 001, but in-plane rotated?
Yeah, that's right. That's right. Yeah. Yeah. Took me a little while to figure out what you're. Yeah.
Is silicon nitride magical or any amorphous material in between? So the question is, suppose I took aluminum as a substrate and I put 3 nanometers of silicon nitride on top.
Actually, people do that. They do a nitridation and create aluminum nitride.
No, or suppose I deposited silicon nitride on aluminum.
Yeah, I know what you're getting at.
Can I
Yeah.
just grow on metals? Can I grow on copper? Can I grow on stainless steel? Can I
People have done that to some extent. I don't know how good they are. Yeah. So with my answer would be, with the right layer pre-grown, I think you can grow on metals and anything. Yeah. So as growth proceeds, so then there's a large amount of incorporation of gallium, and gallium nitride proceeds parallel to that silicon nitride layer and in the word side form. And of course the 0001 surface is the lowest energy surface, and that's where it grows. But of course there are add atoms coming from everywhere up the walls on silicon, which has to cross the silicon gallium nitride barrier and so on. And at the same time there's a lot of desorption going on. The nanowire density is controlled by the 5:3 flux ratio and that thickness of the silicon nitride layer. In fact, we can beautifully control the nanowire density with that and with all that, and we can vary the as you see a forest of nanowires here. You can vary the density by a whole range of parameters, all the way from say low 10 to the power 8 to close to 10 to the power 11 per centimeter square. Now, of course, we learn to grow them, but then we optimize our growth by controlling the controlling the substrate temperature. Say if the substrate temperature is too high, then you have segregation effects. If it is too low, then you create defects, point defects and so on. So we arrive at the optimal temperature and the flux ratio, and here is an example of what is optimal. So you can see that about 545 degrees, a flux ratio of 44%, gives you about, in the as grown nanowires, about 43% quantum efficiency, which is not bad. But that's not enough. So we did all kinds of passivation. Now there are other groups doing core shell nanowires. You can grow an aluminum gallium nitride core, a shell around it and so on, but we didn't go that route. We wanted to keep it very, very simple. So we tried silicon nitride and parylene passivation. Parylene is a dielectric, it's a polymer with a diffractive index of 1.66, and it works very well. We use a physical vapor deposition technique, sputtering at room temperature, and it conformally covers everything, and it's good. As you'll see, it's very useful when we actually make devices. And with the parylene passivation, we can enhance the quantum efficiency by another whopping 12%. So we are now at about 56-57% for these nanostructures, and like I said, we monitor everything by doing time resolved and temperature dependent photoluminescence measurements. We measure the radiative, non-radiative lifetimes, and what we see is that both in the disk regions and in the nanowire regions, the enhancement is the same in the quantum efficiency, and that is because the surface to volume ratio is about the same. So what we are really doing is cutting down the density of the surface states and reducing the band bending and all that happens. And we see the same thing with the passivation, both in the disk region and in the nanowire region. The increase in the non-radiative lifetime is by about a factor of 1.6. So again, it's the same result. However, now you may think that to make a light source, a laser or an LED, you increase your nanowire density as much as you can. You'll get more light, more nanowires, more light. Well, it doesn't work that way. In fact, we found exactly the opposite result: more nanowires, less light. So again, that's when I run to Joanna and I said, Joanna, help. And so she did some detailed TEM, and what she found was that you can have coalescence between either two misaligned nanowires or two nanowires whose diameter gradually increases, and especially when we are growing the top p-type layer, we reduce the temperature, and that's when the diameter starts increasing, and so we can have coalescence, and of course that minimizes the surface, and that's energetically favored, and this misorientation is accommodated by the formation of arrays of dislocations, extended defects, stacking faults, etc. And here are some examples. She calls them zipper defects. And indeed, and here you can see the output of an LED where the density is not optimal. They are not all lighting up. And this is cathodoluminescence showing the same thing. So increasing the density of the nanowires really doesn't help. Instead, you form these defects. But one thing I said that, okay, so if you are forming defects, I had learned long ago that structural defects most of the time behave as electronically as deep levels. So go and measure these deep levels. So we did DLTS measurements on these nanowires, made Schottky diodes, and then measured electron and hole traps, and lo and behold, we do see these very dominant electron and hole traps, which are almost the same as those observed in bulk GaN. And what we did was we measured the densities of these traps, and from these densities we calculated the non-radiative recombination rate. Remember that parameter A and R, and with that A and R we then fitted and with the other coefficients, the C coefficient and the B coefficient, we did this ABC modeling, and here are the outputs of nanowire LEDs. All we have done is varied the nanowire density, and you can see that the best devices are obviously in terms of IQE and light output and all are the ones which have the lowest density of the nanowires. And we can fit these exactly with this ABC model, where the A comes from the deep level density. And this is a typical LED as it looks like. In fact, once we had this technology down well, we knew that we could use this for our lasers. But before I go to the lasers, there was an important question which a lot of people were asking at that time, that all right, fine, we are putting these InGaN disks, what are they? Are they disks? I mean, do they behave like quantum wells? Do they behave like quantum dots? Are they dashes? Are they voids? I mean, actually, we've even found voids. So here are the facts. When we measure in these nanowires and in the self-organized dots that I had talked about earlier, when we carefully measure the radiative and non-radiative lifetimes as a function of temperature, the radiative lifetime, which normally, as we know in any material, it should really stay constant with temperature, shouldn't vary. But it shows unmistakably, it shows an increase with increasing temperature. This is a very abnormal behavior. We made a single photon source with a single disk, InGaN disk in a single nanowire optically, and this is an optically excited thing, and did a photon correlation measurement with a Hanbury-Brown and Twiss arrangement. And here you see a clear anti-bunching behavior, which clearly shows that we have a quantum dot. Here is a high angle annular diffraction measurement, a TEM, of these disks in the nanowires, and you clearly see the formation of a small single quantum dots in these nanowires, and this is a Eales map of that area, and you see the chemical contrast. So that is direct proof that yes, at these compositions of the dots that we are growing, we are definitely forming single quantum dots in these disks. We've done an energy minimization calculation taking into account, this is a finite element calculation taking into account the strain energy, the interface energy and the surface energies of both the InGaN and GaN. And yes, you see the formation, you see the formation of a 30 to 40 nanometer dot in a 90 nanometer nanowire, exact as it shows in the experiments. And in smaller nanowires, they also you will form dots where the dot size will be limited by the diameter of the nanowire. Now, how do you explain all this? So years ago, we had actually seen similar behavior in indium arsenide dots, and this is very well documented now, and others have seen it. The radiative lifetime in quantum dots, indium arsenide or InGaAs quantum dots, the radiative lifetime actually increases with temperature. And the explanation is the following. The main mechanism that cools hot carriers in these quantum dots is not phonon scattering, it's electron hole scattering. This is not an OJ process, it's a two carrier process. And what happens is that a high energy electron, so the first assumption is that the electron states are discrete, whereas the hole states are sort of continuous because of multiplicity and degeneracy and all that. You have multiplicity of hole states. And the occupation of the lowest electron state, which participates in radiative transitions, it depends on two things. One is the rate of this electron hole scattering, and I'll explain what that is, and the occupation of the whole ground states. So what happens in electron hole scattering, think of it at low temperatures, it's easy to understand. So you have a hot electron in either the continuum or in an excited state. It collides with a cold hole, gives its energy to the hole, and it comes down. So it relaxes to the ground state. And the hole, of course, is excited, but then it comes back very quickly by multiphonon emission. Yeah. Oh, the differences. So in the indium arsenide, in the indium arsenide dots, they are larger than the phonon energies, not for the holes. No, no. I mean, the theoreticians are still, you see all kinds of numbers. They are known, but then again, every day you see a new paper. Oh, you mean this way? Yeah, so the offsets in this system are quite large. They are very large. Yeah. Oh, so I'll give you some sort of round numbers. For the red dots, it's about 700, 600 MeV. For the green dots, it's 600, 550. And for the blue dots, no, I'm giving two numbers. So one is the first one is the electron and the second one hole. So it's quite. So as you raise the temperature, the holes actually thermalize, go to higher energy. So there are less cold holes, and these levels are occupied. And so the rate of this electron hole scattering decreases, and so the radiative lifetime goes up. So now this is with the assumption that this energy difference is larger than 91 or of that order milli-electron volt. But it doesn't matter. Even if the electrons are here in the continuum, where they probably are, you would have that bottleneck. In the indium arsenide system, this is very well understood and so on. But at this point, it is just an explanation. However, this is the only way to explain all the results. And there is no doubt that we to explain the increasing radiative lifetime with temperature in this system, and we know that we are forming a dot. All right. So then, since we knew how to make LEDs, so we use the same technology essentially to make edge-emitting lasers. So we grow a laser heterostructure, again the outer cladding layers, the waveguide, and multiple layers of these disks. So this is the first one we tried was a green-emitting laser. So we have 2 nanometer 34% InGaN disks in with GaN barriers and AlGaN cladding, and then an electron blocking layer and the p-type contact layer. So you can imagine this device exactly as a Fabry-Perot laser, except it's made of nanowires. And here's the forest of nanowires, and of course we have learned what the ideal density should be, so we keep it around 5 times 10 to the power 10 per centimeter square. And that's the mode profile. It's quite leaky, but that's the best we can did at this time. But before we made lasers, we did some modeling to see what the photon confinement is, and what the photon modes look like and so on. So we did a 3-dimensional FTTD simulation. We launch a plane wave modulated by that Gaussian into the waveguide, and that's what we see. Now there are some nuances that you see. You see that most of the energy is in between the nanowires, and this is due to the mutual enhancement of 2 evanescent modes in close proximity in the sub-wavelength space. And this is a well-known phenomenon in slotted waveguides and so on. And the other thing is this gap in this direction, and that is because we launch a Y-polarized wave in this calculation, and so that's an artifact of that. But here you see that you do have continuous, there is no blockage in the propagation in this direction. And just to be sure, we made waveguides and did a waveguide loss measurement by measuring the transmission in along different lengths, and we measured a loss which is very respectable, about 7 dB per centimeter. And in the waveguide structures, of course, we didn't do any p-type doping, and we left out the InGaN discs, and we end fire it with green light, with 532 nanometer light. So here's the very short the fabrication. So we grow the dots, and then we passivate it with parylene, and then we do a dry etching with chlorine BCl3 argon, make the mesa, the top contact. Either the bottom contact is on silicon, either aluminum or aluminum gold. And that's what it looks like. This is without the end contacts. We haven't put the end contacts yet, which comes in between. And this is a contact geometry of the top p-type contacts for ground signal ground to do small signal modulation measurements. So if you look at a device, you can't tell whether it's a bulk device or a nanowire device or anything. So these are some of the results from a green-emitting. The first one we made, green-emitting, both CW and pulsed. Here's the spectral output. And we just, after we've done the measurements, we just put it on a toaster and at a CW excitation of 150 milliamps, and said, well, let's just burn it, see how long it lives till it burns. And it was several hundred hours. So the devices are fragile, but not that bad. And then we did modulation measurements also, and actually got very decent small signal modulation bandwidths, about 6 gigahertz, and from these measurements you can extract some of the other parameters. And we determined the differential gain both from the steady state measurements, length dependent, cavity length dependent measurements, and from these measurements by analyzing the modulation response, and there's good agreement. So the K value, if you're familiar with the K value of a gain compression limited device, whereas in the indium arsenide quantum dot devices, the K is of the order of 0.2, 0.3, 0.4 nanoseconds. Here obviously it's much more. Now these are red emitting devices, and the only reason I show you is this. There you see this dip in the alpha parameter that I had talked about long ago, in the beginning of my talk, and that's again some added evidence that indeed we are forming dots in those InGaN disk regions. So the last couple of view graphs now. So then if we can go up to red, then why not go all the way? So make the disks of indium nitride and see what happens. So that's what we did. And of course, growing this is extremely, extremely challenging. We had to change the whole device. So this is half the structure from the bottom just to do PL measurements and so on. So the cladding is a graded, so it's like a Grinch structure where we grow a graded cladding layer in 10 steps, and we do interruption at every step, and we change the growth temperature. We go from GaN to 40% InGaN, and then the active region with 4 indium nitride. These are pure indium nitride discs with 40% InGaN barriers, and then of course we finish it with the same kind of structure. So here is, because of our detector limitations, we could not measure the room temperature photoluminescence, but here's photoluminescence at low temperature. We still don't understand why we get this second peak. My students think it's just a second phase that's there in the indium nitride region. And we made a detector. Before we made a laser, we made a detector out of this. Of course, with the full structure, we made a detector with the idea that if we get a near IR laser, and remember, this is all on 001 silicon, and it's a monolithic laser on 001 silicon. If we get a near IR laser, then you can make a photonic integrated circuit with a waveguide and then a detector with the same material. And the good thing is that the Stark effect will be ideal for the wavelengths concerned. It acts exactly in the right direction. So that's why we made a detector, and here's the spectral photocurrent of such a detector. These are some of the growth conditions that we use, the temperatures and the thicknesses of the different layers. And there's the actual forest. Now, when we looked at the forest a little more closely, we were in for some surprises. It's truly a bimodal distribution. There are 2 kinds of nanowires. One is a very pointed, short kind of things hidden between the larger ones, and so that these are the larger ones, the full complete structures with the indium nitride, multiple indium nitride discs, and you can see this beautiful hexagonal shape. And here is a lattice image of the nanowire showing the good crystalline quality. Now, these pointed, shorter nanowires, we don't know exactly what is going on, but what we think right now is when we form the indium nitride, there are multiple phases. There are many facets, and some of those facets probably have a larger vertical growth rate than the lateral growth rate, and so it becomes more and more conical, sort of cone shaped. And then in fact we have even seen now a shell form. When we grow further on those short ones, there is a core shell automatically forming. For our purpose, they are useless because we are forming the diodes with the full structures. And to our surprise, we are not going to publish this because I want confirmation with more devices. But nonetheless, these are results we got very recently with that structure, with exactly that structure that I showed you. And these are lasers working very decently at 1.3 microns and with very high T naughts, not in a very wide temperature range though, and it has some finite lifetime. And we could even modulate these devices, do small signal modulation, and do these measurements and so on. So these are 1.3 micron monolithic lasers on 001 silicon. And I think as we improve the technology all the way from growth, we have a lot of understanding. I mean, we are really defying nature here. I mean, we are growing these indium nitride discs. We just did it as in sort of brute force mode. But we now have to really understand what is going on, improve the structures, improve the contact technology, and so on, before we can really claim that these are, and then they will be very promising for silicon photonics. So with that, I'll end. Thank you.
Thanks.
Can you comment on the P-type properties of the indium aluminum nitride you grew and the kind of growth conditions you used for that?
So in the bulk, we grow them at 497 degrees. And we dope them in the cladding, of course. We don't dope them very heavily. It's about 1E17, high 16 to 1E17. And in the bulk structures, we are growing them at a slightly, I mean, in the nanowires, we are growing them at a slightly higher temperature, a little over 500. Yeah. Yes.
Was the lifetime data at room temperature or a higher
Yes,
temperature?
everything
Okay.
was room temperature.
Okay.
Yeah. Yes. Go ahead.
You mentioned the measurement of the alpha factor dropping to 0. Have you ever measured negative values for alpha?
No. Yeah, I've seen the papers. Yeah, but no, we haven't. No. No. Yeah, there's one here.
You showed the 5 LEDs that had you were showing the color properties of the 5 different LEDs. Were those different variations in the growth, or were they the same growth but different variations on the same sample?
You mean that converter LED that I showed you?
Yes.
Yeah, the blue dots and the red dots are grown at different temperatures. The blue dots are grown at higher temperatures. I forget. I mean, there's so many. About 500. Yeah. 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 They were completely different structures. Yeah, there were 5 different LED. Yeah. Thank you.